everyone, and welcome to the video 3 of S-block levels. So for today we are going to take a look into the different uses of alkali metals, followed by we are going to take a look with respect to the alkali metal compounds and their different characters. Okay, and we are going to end up the entire video taking a look into the differences between the alkali metal and the lithium atom, followed by what are the similarities between the lithium and magnesium, which are actually very important for the theory exam point of view. Alright, so let's start with the first one, and that is going to be as the uses of alkali metals. So the uses of alkali metals is actually very important section for your 2-mark subdivision when it comes to the theory examination. Alright, in most of the times in annual examination this question has appeared. Give 2 uses of alkali metals. Okay, so we are going to discuss a few of them from which you can write few in examination. Alright, so as we start, the uses of alkali metal, will start our uses with respect to lithium first. Now when we are speaking about the lithium metal, this lithium metal is actually used in preparation of alloys, useful alloys. Okay, it is also used in the thermonuclear reactions. When we are speaking about different alkali metals, such as, let's take over here as sodium. Now sodium is also used in the preparation of alloys such as sodium lead alloy, NaPb alloys. Okay, now it is used in preparation of these alloys because through these alloys we can prepare compounds such as, now here PbMe4 represents that Pb is lead, Me is methyl, it's a methyl group. So we have 4 methyl groups. Okay, so we call this as tetramethyl lead compound. Okay, while it is also used in the preparation of PbEt4. Okay, that is tetraethyl lead compound. So these particular compounds are formed from the alloys of sodium and lead, which were used, actually they were used before in petrols, in the fuels, okay, as anti-knocking agents. Of course, now whatever the petrol that we get are lead-free petrols. Okay, so therefore what happens is when we are speaking about sodium, sodium is used in preparation of alloys such as sodium lead alloy, from which we are going to get the organo-lead compounds, that is such kind of things. These particular things were used as an anti-knocking agent in petroleum products. Of course, now whatever the petrol that we get is free from lead additives. Okay, so taking a look into the next one as this liquid sodium. Okay, this liquid sodium is used as the coolant in fast breeding nuclear reactors. So they are used in nuclear reactors. Now coming forward with the next one, and that is going to be about KCl, potassium chloride. Potassium chloride is used as fertilizers in agricultural sectors, while potassium hydroxide is used as in preparation of soft soaps. While when we take a look into cesium, okay, so cesium is usually used in devising photochemical cells. So it is used in photochemical cells. So these are the different alkali metals and how we do usually use them. Okay. So, moving forward with the next section, and that is going to be the general characteristics of alkali metal compounds. Okay, so the general characteristics of alkali metal compounds. Now we are going to take a look into the different types of compounds that it is going to exhibit and what happens upon the reactions. So starting with the first one, as what we have here is the oxides and hydroxides of alkali metals. Now, first thing that we have to understand that is the different alkali metals form different types of oxides. Okay, now once the oxide is formed and if we hydrolyze these particular oxides, now hydrolysis in a sense, once the oxide is formed and if we react this oxide with water, that particular process is called as hydrolysis. Okay, upon hydrolysis, we are going to get hydroxides. So remember this, whenever we have oxides, whatever type of oxide it may be, so whenever we have oxides of alkali metal, okay, so these oxides of alkali metals, upon hydrolysis, what is going to happen is, upon hydrolysis, it is going to end up giving us hydroxides. So, hydroxide is any compound which is going to have as M represents, let's say, an alkali metal. Okay, hydroxide is nothing more than a metal connected to OH group. Okay, hydroxyl group, this is what we call it as. Now, taking a look into lithium. So when we have lithium has a capacity to form only oxides. Okay, though if you react this particular lithium with excess of oxygen, it's not going to combine with more amount of oxygen. Okay, so therefore, lithium has a tendency to form lithium oxide, Li2O. While if we take into consideration of sodium, sodium has two possibilities. Either it can form sodium oxide or sodium peroxide. So, sodium oxide, it can be given as Na2O, while sodium peroxide can be given as Na2O2. Okay. While if we have different metals, now here different metals I am going to speak it as M is nothing more than potassium, rubidium and cesium. When we take these three sections, okay, when we take these three metals, that time what we understand is that these metals have a capacity to form superoxides, and superoxide is denoted as MO2. So these are superoxides. Oxides, peroxide, superoxide. Okay, so now as we have said that any oxide, any type of oxide upon treatment with water ends up giving us metal hydroxides. Let's observe. Let us say that we have, so here let's speak about M2O, that is metal oxide, upon treatment with water. What happens here is this particular metal oxide converts into metal hydroxides as MOH. Okay, now let's observe how many metals do we have here is 2 metal ions. So 2 metals, 2 metals, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. Correct? So let's observe one example here, as in the case of lithium oxide upon treatment with water. Okay, it is going to form 2 lithium hydroxides. Now this is for simple oxides. Right? Let's observe the second case. This is the case number 1. Let's observe the second case, and that is going to be M2O2. M2O2, that is a peroxides. Now, whenever we have peroxides and we react this one with water, what happens is we get 2MOH, right, because of 2 metals. Along with this, we end up getting over here a byproduct as hydrogen peroxide. Okay, so let's observe whether it is balanced. We have 2 metals, we have 2 metals. 2 oxygens here, 1 oxygen here, that means there are 3 oxygens on my reactive side. 2 plus 2, 4. That means I need to get over here as 2. So 2 plus 2, 4 oxygens now. 2 oxygens here, 2 oxygens here, 4 oxygens on the product side. Perfectly balanced with respect to oxygen. 2 hydrogens plus 2 hydrogens, there should be 4 hydrogens, and therefore 2 into 2, 4. Correct? Let's observe, taking one example over here as sodium peroxide, Na2O2 plus 2H2O. Upon hydrolysis, it will give us NaOH 2 times plus what we are going to have is hydrogen peroxide as a byproduct. This is how the reaction goes. Coming forward with the third category, and that is going to be with respect to MO2 plus H2O. Okay, so now we are going to take over here superoxides into consideration. When we take superoxides and react this one with water, here we are going to get, of course, metal hydroxides. Along with metal hydroxides, we are going to get 2 byproducts. The 2 byproducts that we are going to get here are going to be water molecule, it is going to be hydrogen peroxide. Along with hydrogen peroxide, there is going to be the liberation of oxygen molecule. Now, in order to balance it, let's observe. So, let's check the number of oxygens first. 2, 2, 4, 5. So 5. So 2. Here 2. So 1. So in order to balance this, let's take here as 2, 2. So 2 into 2. 4 oxygens, 4 plus 2, there are 6 oxygens on the reactive side. On the product side, what we have here is 1, 2, that is 3, 4, 5. Let's make this here. So 2 oxygens plus 2 oxygens, 4 oxygens plus 2 oxygens, 6 oxygens, perfectly balanced with respect to oxygens now. Now what we have is hydrogens. Let's check the hydrogens. We have 4 hydrogens on the reactive side, 2 plus 2, 4 hydrogens, perfectly balanced. 2 metals, 2 metals. So this was for your superoxides, right? So let's take one example over here as potassium superoxide on reacted with water forms potassium hydroxide. Along with this, we have here is hydrogen peroxide. along with the hydrogen peroxide, we are going to get over here oxygen being liberated. Now, in order to balance it, let's take over here as 2 and let's take over here as 2. So this was the section for the super oxides. Well, this was with respect to the pearl oxides. Okay, so let's observe character number 2 now. The next general characters of the alkali metal compounds with respect to halides. Now, first thing is how halides are formed. Okay, here we need to understand that whenever we have any particular compound of alkali, appropriate compound of alkali, such as we have an alkali oxide, or we take over here alkali hydroxide, or we take over here alkali carbonates. Okay, when we have these and as we react these with HX, that is hydrohalic acids. Okay, so or you can also call them as halogen acids. When we react these particular things, that is alkali oxides or alkali hydroxides or alkali carbonates, appropriate ones, with hydrohalic acids or halogen acids, what happens is we are going to end up getting over here alkali halides. When this particular compounds are formed, a large amount of energy is liberated. Okay, as a large amount of energy is liberated, we denote this as delta H. Delta H represents the enthalpy of reaction. How much amount of energy, whether it has been liberated or whether it has been consumed. If it is liberated, we represent it as by negative sign. If it is consuming the energy, if it is taking energy from the atmosphere, we give it as delta H as positive. Okay, so now here delta H is negative, that means it is going to give away energy. The compound which is going to be formed is going to be stable in this particular case. Okay, and we usually denote this as delta HF naught. That is, the standard enthalpy of formation is negative. That is, a lot of amount of energy is liberated. But it differs from one halogen to the another halogen also. Okay, now here what we have to understand is, if I am going to take that we have this particular metal and the metal is connected to different type of halogens. Let's say metal is connected with fluorine, metal is connected with chlorine, metal is connected with bromine, and the metal is connected with iodine. Okay, now what happens is the amount of energy liberated when this particular metal fluoride is formed is far more greater than the metal chloride's formation. Okay, this thing is far more greater than this one. This is far more greater than the last one, that is metal iodide. That means the least one is the metal iodide. In short, what we have to remember is, as we travel down the particular group for a given metal connected to different halogens, here delta HF naught goes on becoming less negative. It goes on becoming less negative, in a sense the value goes on decreasing. Amount of energy that is expelled, that is liberated, goes on decreasing. Same is the case when you change these particular metals also. Okay, so there the energy goes on decreasing. Okay, so in case if I am going to take over here, let's say lithium, okay, followed by what we have is sodium, followed by potassium, rubidium, cesium. Okay, now let's say these are connected to fluorine. So all of these are connected to fluorine over here. lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride and cesium fluoride. Again, when this is formed, as we travel down a particular group with respect to the alkali metals, again here the same thing repeats. That is, the energy liberated delta HF naught is going to be less negative as we travel down the particular group. Okay, this is how it affects. Now, we'll take a look into its solubility. So, as we have seen about the different halides, the amount of energy that is liberated once the reaction is done, how it varies in a particular group. We have already seen that. Now, let's observe its effect on the solubility. That is, whenever we have the halides, all the halides or the alkali halides are actually soluble in water. Okay, so they are quite water soluble, but there are certain exceptions. Now, exceptions in a case of, if we observe closely with respect to the lithium fluoride. Okay, and the second one what we have is the cesium iodide. These are the two extreme compounds which are going to differ a lot with respect to the stability or with respect to the solubility in water is concerned. So here, when we observe about the first case, that is the lithium fluoride. Now, lithium being a smaller molecule and fluoride being a smaller ion. What happens there is, these particular things, when they combine, when they form the crystal, okay, when they form a crystal, once they form this, a lot of amount of energy is liberated. As a lot of amount of energy is liberated, they form a crystal in very perfect manner. Therefore, we call this particular energy over here as the lattice energy. So, in short, higher the energy that is been expelled out, the better the crystal is formed. Now, that particular better the crystal is formed or the lattice structure is formed, okay, more is the energy need to be expelled out. So, as it has a very high lattice energy, okay, so once we put this particular thing, this crystal into water, it is less soluble. So, it is less soluble because of higher lattice energy. Okay, now on the other hand, about cesium iodide is concerned, because of the larger ions. The ions are quite large. Cesium, bigger size. Iodine, again a bigger size. Okay, so what will happen here is, because of the larger sizes of cesium as well as the iodide ion, here these particular cases are having low hydration enthalpy. As it has very low hydration enthalpy, it is not capable of combining with water easily. As it is not capable of combining with water easily, again because of this particular reason, cesium iodide becomes less soluble in water. Okay, now for the competitive exam, remember one simple rule. For any given ionic compound, okay, it is the hydration enthalpy. The hydration enthalpy, that is nothing more than the amount of energy that is going to be released once the ion comes in contact with water. Once it attaches itself with water, the amount of energy released, okay, that should be greater when we compare to that of the lattice energy. Okay, so this is the phenomena what we need to remember. If this particular thing is satisfied, then the compound is quite soluble in water. Okay, so this is the thing what we have to remember for the competitive part. Alright, so moving forward with the next one. Coming forward with the next section of discussion, and that is going to be the salts of oxo acids. Now, oxo acids, first we'll understand what exactly is an oxo acid. So here, whenever we call a substance as an acid, okay, that particular substance has a tendency to donate H plus ion or a proton, right? It donates that particular H plus ions. Now, in case if this H plus ion which has to be donated from an acid, it is attached to hydroxyl group. That means it is going to be donated from an hydroxyl group. Okay, for example, we have as H2SO4 sulfuric acid. Okay, so we have that. We have H2CO3. So such kind of acids wherein H plus ion is connected to OH group. Okay, so it is actually this hydrogen that is going to be donated off. Such kind of acids are called as an oxo acids. So these particular things are nothing more than simple oxo acids. Now, when we have an oxo acid and this oxo acid reacts with an alkali metal, okay, as it reacts with an alkali metal, the product of this reaction would be a simple salt. Now, this salt can be a carbonate or it can be a bicarbonate. Okay, now carbonate CO3 minus 2, bicarbonate or what we can call it as an hydrogen carbonate. So that one is HCO3 minus 1. Okay, so now whenever oxo acids react with alkali metals, it will give us salt. The salt can be either carbonate or bicarbonates. And these particular things are much more stable to heat. Okay, so as we travel down the periodic table in an alkali series, that is from the lithium to sodium, potassium, rubidium, and of course cesium. What happens here is, as we travel down, the electronegativity, or we will call it as an electropositive nature, positivity, this thing increases. Correct? Now, this increase in an electropositive nature has a direct impact on the stability of carbonates and bicarbonates. Okay, so as electropositivity increases, stability of carbonates and bicarbonates will increase. Alright, they are going to increase. That means if we observe the first section, and that itself is the lithium. Okay, so this lithium, when it is going to form a carbonate, lithium carbonate, okay, it is not stable to heat. It is not going to be stable when you subject it to heat. So, lithium carbonate is not stable when subjected to heat. Okay, that is, if you subject this thing to heat, it decomposes. That is, lithium carbonate upon subject to heat decomposes in order to form lithium oxide and gives off carbon dioxide. So this is how the entire reaction happens here with respect to the lithium is concerned. This is what we get. Alright, so this is with respect to the lithium carbonate. Moving forward with the next section, and that is going to be the anomalous properties of lithium. Again, very important for our theory exam points. Alright, so as we start with this, first thing that we have to understand is that why does the lithium shows the properties which are not similar to that of the alkali metals, and that is why we call it as anomalous properties, right? So when we speak about lithium over here has two such important properties which makes it distinguished, okay, which makes it unique when we take a look into the entire section of alkali metals. These two properties are, the first one is with respect to its size. So when we take a look into the size of this particular lithium, what we see is the size is exceptionally small. It is exceptionally small with respect to the size of atom or ion. Ion sizes are much more smaller when we compare to that of the atom. Okay, so due to the exceptionally smaller size of atom and ion, it is going to show us anomalous property. And second one is because of its polarizing property. A high polarizing capacity or capability, as you can say. Here it is nothing more than the ratio of the charge to its radius, and this is nothing more than the polarizing property or high polarizability of this particular lithium is been concerned. Due to this, it is going to show us anomalous properties. Now let's discuss what are the different anomalous properties of lithium are. First thing, when we take a look with respect to lithium, okay, lithium occurs to be a harder metal when we compare to the rest of the alkali metals. The alkali metals are known for their soft nature. Okay, those are the soft metals, but here lithium is a hard metal. It is a hard metal having a good or high melting point as well as the boiling point is being concerned. Okay, so quite high melting point and boiling points. So therefore, second one is it is going to be a hard metal, which is again not in accordance with respect to the alkali metals are being concerned. Now, second one, as we see, lithium. It is least reactive. It is least reactive in nature, but it is a very good, stronger reducing agent than the other alkali metals. As we take this lithium and if we burn it, combust it in the presence of air, this lithium has a capacity to produce two compounds. That is, it forms lithium oxide and lithium nitrate. Okay, lithium oxide and lithium nitrate. So, Over here, the other compounds are not capable of forming lithium nitride. Remember this, they will form only lithium oxide, alkali oxides. So, coming forward with the next one. When we take a look into lithium chloride, okay, lithium chloride is deliquescent in nature. The crystals here, what are forming, have a very high hydration enthalpies, due to which it always remains hydrated. It forms from an hydrated solution. Okay, and we get over here in the form of lithium chloride dot 2H2O. Okay, this is how lithium chloride exists. Furthermore, when we take a look into lithium hydrogen carbonate, or we can also call it as lithium bicarbonate, this will never exist in the solid form. It will never exist in the solid form, and that is a very important aspect, because all other alkali bicarbonates exist in solid form, but lithium bicarbonate will never exist in a solid form. Okay. When we take into consideration of such as lithium nitrate. Okay, so lithium nitrate here, upon combustion, what happens is this decomposes. When it decomposes, it gives us lithium oxide. Along with lithium oxide, we have byproduct, that is nitrogen dioxide, along with oxygen that is getting evolved. Okay, in order to balance that, we'll take over here as 4 lithiums. So 2 lithiums here, 4 nitrogens, okay, and oxygen over there. So total number, let's observe with respect to oxygen. 2 oxygens here, 8 oxygens here, so 2 and 8, 10, 10 plus 2, 12. So 4 into 3, 12. 4 lithiums, 4 nitrogens, 4 nitrogens. Perfectly balanced. Okay, so when we observe lithium nitrate, so lithium nitrate has decomposed in order to give us lithium oxide and nitrogen dioxide along with oxygen. But if we have the other alkali metals such as sodium nitrate, okay, let's take over here sodium nitrate, and as we heat it up, as we heat this sodium nitrate, it will decompose in order to give us NaNO2. Okay, it is called as sodium nitrate. Along with this, oxygen gets evolved. Okay, in order to balance, let's take over here 2. So 2 into 3 is 6. 2 into 2, 4. 4 plus 2, 6 oxygens. 2 sodiums, 2 nitrogens, 2 nitrogens. So here, the other alkali nitrates, they are decomposing in order to give nitrites, while over here it is forming oxides. That is the prime difference between the lithium and alkali metals are being concerned. Coming forward, taking a look into the points of similarities between the lithium and magnesium, we already know that with respect to the diagonal relationships, lithium and magnesium, they exhibit almost similar characters, similar properties. So therefore, let's see what are those particular properties. In the first case, both lithium as well as magnesium is been concerned. Both of them are the lighter and hard elements in the respective groups are concerned. Okay, both of them are light and hard. elements. Second thing that we have to understand here is both of these, that is lithium and magnesium. They are not going to react quickly with water. They are rather less reactive with water. Okay. Second thing that what we need to understand here is their oxides and hydroxides. Are less soluble in water. And further, if we observe that their hydroxides decompose on heating. As they start to heat this particular hydroxides of lithium and magnesium, they will start to decompose. Furthermore, if we observe lithium and magnesium upon direct reaction with nitrogen. If we take nitrogen and we react this one directly in combination with lithium and magnesium, it would form nitrides. Okay, it is going to form nitrides. That is the lithium nitride and magnesium nitride. Alright, so coming forward, when we take lithium and magnesium oxides, and if we try to react this one with excess of oxygen, okay, if you take simple lithium and magnesium and you try to react that with an oxygen, it would lead to the formation of lithium oxide and magnesium oxide. It will not give you super oxide. It will never give you super oxides. Furthermore, if you observe the hydrogen bicarbonates, or we can call it as a hydrogen carbonates of lithium and magnesium, we will find that in this particular case, they will never exist in a solid state, rather they exist only in the liquid state so far as lithium and magnesium hydrogen carbonates are concerned. Okay, finally, both lithium chloride as well as magnesium chloride, both of these are deliquescent in nature. They are formed from the hydrated solutions and they exist in the hydrated form. They exist in an hydrated form as first one, lithium chloride dot 2 H2O and magnesium in the form of MgCl2 dot 8 H2O. Right? Because of its hydrating nature, both of these are going to exist in the form of the hydrated forms. Okay, so this is the end for today's video. Take care.